All right, there we go. Hopefully we're not going to have problems with connection today. I have a feeling my internet speed is a little lower than is ideal. Hope you like the t-shirt. All right. Can you all hear me?
Hello.
Yeah, there we go.
Yes, sir.
Aha, I got a cool word of the day for you. Let me just show you what one of those looks like. Oh, come on. Yeah, there we go. Yeah, look at that.
Is that dead space inside the box?
Oh, fuck knows what it is. It's supposed to be a tesseract. And so this all came from, I was reading up about, bloody hell, where's the chat thing gone? Watched Interstellar on Monday night, I think it was. Yeah, Monday night. Again, and there's a tesseract in there, so I was reading through some of the science behind so the physics that they showed during that film. And there's actually, I was wrong. There weren't 2 research papers. There are 3 research papers published from that film. But anyway, one of the things that is in the film is what's called a tesseract. And according to Wikipedia, a tesseract is essentially the same to a cube as a cube is to a square. So it's a 4-dimensional cube. And anyway, don't ask me any more than that. That's kind of about the limit of my understanding of it. Isn't it cool though?
I was literally about to ask you to elaborate.
No, don't.
It's all good.
No, I mean, pretty much for the last quarter or a third of the film, all I heard from my kids was groaning and complaints about how their heads hurt. Because, yeah, I mean, has anybody watched it yet? Anybody done their homework?
Oh yeah, loved it.
Yeah. Oh, good. Paul, have you watched it yet?
I haven't, because so it's on Netflix in France, and I don't have a VPN to say that I'm in France, so I haven't gotten around to it yet.
That's a pretty poor excuse.
Well, it's better than finding other less than legal means.
Oh yeah, I totally wouldn't condone that. That's a terrible thing to do. Anyway. Oh, and there's also a whole bunch of stuff on the black hole in the film called Gargantua. I think that's a little bit silly as a name, but like some of the physics of like gentle black holes, it's just crazy, absolutely crazy. Anyway, so that was a fun thing to do. So essentially, I'm not sure where we'll get around to all of it today, because let me find out where the hell's the chat gone. Come on. I'm getting a little bit less enamored of Zoom as time goes on. I might have to. Come on. I just want to make sure I don't miss anything. Oh, for fuck's sake. There we go. Back again. All right, Zoom chat. Yes, like from the Avengers. I'm not sure the makers of Marvel films. There we go. Finally. followed the same degree of scientific rigor in their use of the Tesseract that they did in Interstellar. But yeah, same kind of thing essentially. Not necessarily an Infinity Stone, but anyway, one of my favorite things reading about Interstellar is that the astrophysicist, or it was actually a theoretical physicist, who was the chief scientific advisor, a guy called Kip Thorne. He laid down 2 rules where that were, would have to be followed if he was to work on this film. One was that no physical laws could be broken, which is like a man after my own heart. I hate sci-fi when like things don't work the way they should do in kind of basic physics. And the other one was that any kind of like crazy stuff should come from science rather than from just like artistic license. And supposedly he spent 2 weeks arguing with, what's the director's name? Chris Nolan, I think.
Nailed it.
Yeah, because Chris Nolan wanted to have one of the characters travel faster than light, and he basically just badgered away at Chris Nolan until he gave up and didn't put it in the film. So yeah, that's pretty cool as far as I'm concerned. Anyway, so essentially there's kind of 2 things I want to talk about today. One is the Proxima b, right, which is a planet. It's orbiting around Proxima Centauri, which is the closest star to Earth. It's a wee bit less than 4 light years away, which is, I mean, that's basically like Hondo, or one of the small towns, Bandera maybe, in terms of kind of galactic distance. It's really, really close, and kind of close enough that if we could get something there, that we'd be able to get information back within a manageable time frame. If we use high-powered lasers, we'd get that information back in 4 years, basically. Whereas most of the other things that we've been looking at are just so far away that we can barely even visualize them with telescopes. So essentially, this was a kind of public science campaign, which is kind of neat, called the Pale Red Dot, and it's basically kind of a way to engage people in astrobiology, astrophysics too, I guess. But also there's a big effort to try and find, hopefully, a planet around Proxima Centauri, and they actually did, right? So it's called a pale red dot because, where's it at? There you go. I don't know if you can see this well enough. It's kind of a small picture. Let's blow this up a bit. Let's see. Okay, so Alpha Centauri are a binary star system. This is kind of a trinary star system. It's a little bit weird. Essentially, you have 2 main stars. Like Alpha Centauri A is pretty big. It's kind of like a Sirius, not Sirius, Sirius, as in Sirius Black, not a Sirius Black. Size star, so it's like an O class, maybe a little bit smaller than that, and a smaller companion star called Alpha Centauri B. And then around those 2, you have Proxima Centauri, right? So basically, these 2 orbit around each other, and then Proxima Centauri orbits around that, right? Which is, pretty weird. And this is the relative sizes of those stars. So Alpha Centauri is this pretty big star. It's bigger than the sun is. Alpha Centauri B is a little bit smaller than the sun. And then Proxima Centauri down here is just a wee smidgen bigger than Jupiter. Right, so again, that kind of hammers home how bloody big Jupiter is. It's an enormous planet, and also how size is not the defining factor, right? So Jupiter is huge and it's massive, but it's not very dense because it's a gas giant. And so Proxima is not much bigger than Jupiter. It's the same for TRAPPIST-1, which we'll look at in a little bit. There's many, like 50 times denser than Jupiter is. So that's why it's a star and not a planet, amongst other reasons. Anyway, so Proxima is a red dwarf, and actually finding, exoplanets around red dwarfs is fairly, I wouldn't say easy, but it's easier, right? Because essentially they're less massive, so radial velocity or Doppler photometry is easier, right? Because there's a smaller relative difference between the mass of the star and the mass of the planets, right? So the star is more likely to be wobbling. And also, if you think about transit photometry, you know, either you need a bigger planet or a smaller star, and you'll get a bigger dip in the brightness, right? So red dwarfs are actually a pretty reliable source of exoplanets in terms of the searching that we're doing. So it's not a big surprise that we found something around Proxima, but it's still pretty cool. So essentially, so one reason why we care about Proxima is because it's close. Really, that's the main deal. It's not really predicated on what we know about Proxima b. It's really just the fact that it's at least manageable conceptually, just maybe a little bit, that we could actually get there, right? So, so I was watching this funny animated cartoon yesterday about getting to TRAPPIST-1, which is, I think, 40 light years away, about 10 times as far, traveling at the speed of a New Horizons probe, which was, apart from Juno, the fastest man-made object. It would take us 813,000 years to get to TRAPPIST-1 at the speed that that probe was going at. That's a really, really, really long time. Like a really long time. So maybe it would be a little bit less for Proxima. So anyway, and we'll talk about that on Monday. There's just some fun stuff to talk about, the physical and biological constraints of long distance space travel, which is a fun thing to think about, in my opinion. Anyway, so they were able to find Proxima b by Doppler shift, right? So that's that change in light frequency output of a star based on its kind of wobble, basically induced by its companion planet. And obviously a lot of stuff kind of came from that, right? So it's a lot closer, so we're able to observe it much more readily. We have a lot more information on it, as you know, best as we can. It's still not trivial to observe these places. 4 light years away is still a pretty long way, right? Anyway, so obligatory red dwarf poster. I don't know, most of you are way too old, too young to remember Red Dwarf, but it was a comedy when I was growing up.
Good show.
Have you watched it?
Yeah, it's on or it was on Netflix. I don't know if it still is.
Really? Oh, I might have to go for a walk down memory lane and go watch some of that. It was pretty cheesy, that's for sure. Very low rent. Anyway, so essentially when we look at Proxima Centauri, and this is something that applies to TRAPPIST-1 too, and a lot of red dwarfs. Red dwarfs are pretty different from our sun, right? G-class star. So our sun has a whole bunch of different layers to it, many of which I can't remember. And it has a various range of convecting and non-convecting layers, right? There's the photosphere, the troposphere, there's coronosphere, which is kind of funny given current situation. Whereas red dwarfs are a lot simpler, right? So red dwarfs tend to be convecting from their core, right? So this is a artist representation essentially of what a red dwarf star looks like internally. Very different from what the sun looks like. Let's see if we can actually. Woohoo! Let's get rid of that because that's making my brain hurt. Oops. Let's see if we can. Yeah, no, don't want that. Yeah, here we go. So, can I get that bigger? That's better. So, yeah, coronal hole. That sounds painful. Anyway, the sun consists of a whole bunch of different layers, right? So we've got the convective zone is kind of the outer one, so that's what causes sunspots, where material goes into the sun and it gets cooler, and then also one of the reasons for flares, essentially. You've got a radiative core zone, and then you've got a core, and there's a whole bunch of more stuff going on. So when you look at red dwarfs, it's a lot simpler than that, right? And so what that actually means is that these stars are much less stable. And so even though they have a lot lower output in terms of luminosity and temperature, their output is generally much more variable than our sun is. And their name is essentially, they're typically called flare stars. So they have very kind of, I wouldn't say periodic because that has other connotations, but every so often they'll have a massive flare, right? And so like a coronal mass ejection where they kind of just spew out solar material. And which one was it for? I think it was for TRAPPIST. Let's get notes back up. Oh yeah, there's TRAPPIST-1, but the same kind of applies to Proxima b. I don't know if you remember me talking about the Carrington event, which was a massive solar flare in the 1800s sometime. I can't remember the exact date. But basically it was a solar flare that was so powerful that it powered telegraph lines in the US without electricity. So telegraph operators were able to send messages between, I think it's like Boston and New York or something like that, without the equipment actually plugged into the main circuit and powered on, right? So that was kind of gives you an idea of how massive the amount of charged particles were that they were able to actually power electrical equipment on the ground. And so those occur fairly frequently. So it's a very interesting thing to consider, because obviously that's not good, for life. It's kind of good to have some radiation, right? Because radiation causes mutations, and that causes the basis upon which natural selection acts. So you get evolution. But evolution kind of has its limits, and it requires things to live, right? So the properties of these red dwarfs, even though it's more likely we'll find exoplanets around them, they're potentially far less hospitable places to live, maybe, right? And so we can talk a little bit about that when we look at the TRAPPIST system later. But another really interesting thing to think about is that because red dwarfs are, it's a shame they did the lettering so tiny on these images, because they're super cool images. It's kind of squished a little bit, but because red dwarfs are so much cooler than our like G-class stars, their habitable zones are way, way close to the star, really, really close. And so this is our solar system. This is Mercury. I don't know, Venus is kind of about where slide 11 is over here. And Earth is gently perched on my couch cushion, kind of over there, right? And the whole habitable zone of the Proxima system is kind of within a tiny fraction of Mercury's orbit, right? So, and Proxima B actually orbits within its star's habitable zone, right? So they're potentially, if all of those solar flares didn't strip all the atmosphere off, potentially Proxima B could have water on its surface, right? At least based on mass and temperature. And how, yeah, its orbital period is about 11 days. So that's another common theme, right? These things orbit so close to their star, they're constantly like that around the star. They've got very quick orbits. Anybody got any questions so far? Observations? Desires to send spacecraft there with bacteria? Sorry, Kiara, I shouldn't keep going on about that.
I still think that's a really good idea, and I don't understand why not.
Okay, objection noted. Kiara.
So I know you talked about the wave from the 1800s that powered the telegraph lines. Did it get so powerful that it like knocks out all electricity due to EMP?
Yeah, I mean that's the fear of coronal mass ejections, right? There was one fairly recently, which just because of our orbit it missed us. But if we were to be hit by and there have been flares that are larger than Carrington event. It's just called an event because it hit the Earth, right? So the sun's flaring all the time to varying degrees. It has there's a solar cycle of activity, you know, sunspots and also flares and things like that. But yeah, there was a coronal mass ejection in the last couple of years, which if it had hit us, would have knocked out all power on the Earth, which is
exciting.
Yeah, that's kind of almost an end of civilization kind of great event.
We'll be back.
If you think about how all commerce and finance and defense and everything is electronic, right? Yeah, it's kind of scary, actually. Best not to think about that is my approach, because there's nothing you can do about it.
There's a show called Revolution that's kind of along that lines.
Yeah, I mean,
Yeah.
it's like any good sci-fi is always based on sci, not fi, in my opinion. And yeah, and so there's a kind of it's like I don't know. So when I answered talking about Robertson's question last class about are we alone, and so you need change for life to emerge, and that's actually I don't know if you remember from Interstellar, that was an argument that one of the scientists, Dr. Brand, played by the absolutely lovely Anne Hathaway. Probably better not get into my actress crushes right now, not during class time anyway. Anyway, she argued after the fact that it's unlikely that life would ever emerge really close to a black hole because it just reduces random chance, right? It pulls in everything. And so the flip side would be for red dwarfs, which are much more random in their activity. Maybe that's enough random variation that life does emerge. Maybe those flares are sufficient that anytime it does get a chance, you know, a massive flare occurs and it wipes out emergent life on that planet. There's not really any way of knowing until we go there and have a look around and see what we find. But yeah, it's cool stuff to think about, that's for sure. Anyway, yeah, any more questions? Got a little bit of funky stuff to do before we get onto the TRAPPIST system.
Oh, okay. That was my next question about the
Pedro,
TRAPPIST.
you're going to have to speak up a little bit. I can't hear you very well.
That was my next question. And what's the specific question you're asking about Proxima B in the TRAPPIST system? Like, is there like a certain relation that you want us to know or something? There's not really a question. That's why.
Oh, okay. More like where am I heading with this kind of thing? Is that what you're interested in?
Yeah, sure. I just wasn't sure. Like, what's the question on the study guide?
Oh, okay. What is on the study guide? Oh yeah, haven't done it yet. Ha. That'll be done after class today. So essentially, the reason why I'm bringing these up is people care about Proxima b because it's close, right? So we could study exoplanets till cows come home, and it's largely theoretical if we've got absolutely no hope of even getting a probe there, right? So that's why a lot of effort went into trying to find a planet around Proxima Centauri, because it is the closest star. And actually, it will be in 25,000 years, it will be even closer, because of the relative motion of the different stars and the like. So that's one big reason, because if that does have a planet around it and it is habitable, then maybe one day in the future we'll go there. So that's why Proxima b is so exciting, right? It's kind of tantalizingly close. I mean, it's not close, but one can start dreaming about how it would be possible to get there and actually explore another planet around another star. And it's kind of, I don't think you can really overstate that too much, right? We're not talking about other planets in our solar system, right? Because we're here. We're talking about other planets in other solar systems. So what's there, right? Not just can we go there and live there if we screw up our own planet, but more, is there other life there? And, the only way to know is to go, basically. The reason for looking at the TRAPPIST system is because it's a solar system. I mean, there are some solar systems out there that we've defined, but nothing like the TRAPPIST-1 system, right? And so, and also one reason why I like it is it's very much like the Jovian system, right? There are an enormous number of similarities, right? So what we know about the Galilean moons, we can apply to the TRAPPIST-1 system and vice versa. And so we can actually start doing a lot more detailed modeling of what those environments look like, which also, again, leads to the question of, is there life there? And I think one of the, probably, and this is more philosophically speaking, I think one of the biggest questions of all humanity, and this has actually probably been since the dawn of civilization, is, are we alone? Are we it? And I think that these two systems are potentially our most viable ways of answering that question. And they're really cool as well, so they're fun to look at. So yeah, that's why I brought those up, and also because they are so interesting, we know so much more about them, and so it's easier to talk about them because there's more to talk about. So it's a little bit of a kind of a circular argument in a sense. Anyway, so obviously a lot of work's been done. Did that answer your question, Pedro?
Yes, sir. Yes, sir.
Cool.
Thank you.
Yeah, they are super cool. So one of the questions is about Proxima b is, what kind of environment is it, right? And so I don't think they've been able to directly measure its atmosphere yet. I'll have to double check on that. I think they're waiting for the new James Webb telescope to go up next year to be able to properly look at its atmosphere. I don't really know quite why, to be honest, why they haven't been able to use the other ones. But anyway, because it's so close to its star, right? So it's in a very, very close orbit. It's almost certainly tidally locked, right? And so we know what that means from the moon, right? So it's always facing the same. Well, essentially, it rotates once every orbital period, right? So it's always showing the same face, is what tidal locking means, basically. And also the same from the Galilean moons of Jupiter and, Charon of Pluto and things like that. But there are different types of tidal locking. And so actually, it's funny that this picture's up. Mercury is also tidally locked to our sun. And so Mercury has what's called a 3-2 orbit. And so it rotates 3 times around its own axis for every 2 orbits around the sun. Right, so it doesn't show the same face to the sun the whole way around like the moon does to the Earth. It kind of varies its face, essentially every other orbit. Yeah, I think that works out right. Math isn't my strong suit. And so that has really big consequences for any environment, obviously not on Mercury because it's a barren, dusty rock, right? As far as we know. But it has big implications for Proxima, right? So essentially, if you get 2 very different environments depending on whether or not it has a tidal locking, a 3-2 resonance, which is what Mercury has. So it rotates Proxima Centauri itself 3 times for every 2 orbits of Proxima Centauri, or if it has a synchronous rotation, which means like a 1-to-1, which would be more like Io or the moon, for example, right? So it's always facing the same way. Let's just see. Oh, hang on. Oh, I'm sorry, Pedro. I missed your question in the chat. Let me bring that up a little bit. Yeah, and obviously that has a really big effect because if you think about if that planet is always facing the same point, you're not going to have seasons, obviously, and you're also going to have one half of the planet at a much higher temperature than the other half, with a dividing line around where the terminator is, right, between the light and dark sides. And so that really doesn't leave many options for life, really, whereas a 3-2 rotation potentially does, right? And so that's essentially what they've modeled here, is essentially figuring out the likelihood of water on Proxima b also depends on whether it has a synchronous or a non-synchronous rotation. So still lots of unanswered questions about Proxima b, but really, really cool. There's actually a cool book about Proxima b called Proxima by a sci-fi author called Stephen Baxter, which I read way before I ever taught this course. So that's well worth checking out if you're otherwise interested. So there's just one planet, as far as we know, around Proxima b. So what about if you have many, right? So that's where we come in with the TRAPPIST-1 system. Right? So this is again one of those NASA holiday vacation posters, and I really like those. I always find them really funny. And so this is kind of a visualization of what it would look like if you're on one of the planets in the TRAPPIST system, obviously at the right point where all the planets align. But it's a solar system with 7 discovered planets, and they're pretty sure it's just 7, but they're not 100% sure. And it's about 40 light years away. It's another red dwarf, right? Which is why it's so dim out there. And 12 parsecs, I don't fully understand what parsecs are. That's a radial separation between two things, kind of equals distance. I don't really understand the math behind it. But that's within about 40 light years. And I've got some really cool bouncing around. Let's see if I can get this working. Maybe. No, I hate PowerPoint when it comes to this shit. Oops. So this is what the TRAPPIST-1 system looks like. So it has 7 planets, and they're all in orbital resonance with each other. So this is very much like, let's see if I can get this one working better. This is, let's see, you gonna work? Come on. This is 2020. Videos and PowerPoint should work a little bit easier than this. So this is what it looks like when it's sped up. So it's a 3-body resonance system. And it's really, yeah, I don't know. Makes my head hurt thinking about it, to be honest. But essentially what they're doing here is they're showing you where those 3 bodies line up, and that alignment kind of walks around the system essentially over time, right? So this is kind of a really neat way of showing that. So it's not a simple resonance like the Galilean moons of Jupiter, right, which are in a 4:2:1 resonance. It's much more complex than that. So essentially, let's get you back. This isn't exactly what it looks like because that sun over there is not to, it's to scale in terms of size, not to scale in terms of distance. But these planets are astonishingly close together, right? They're not quite as close together as to the sun as the Galilean moons are to Jupiter, but it's not that far off. So if you actually look at this comparison, which I think is absolutely fabulous, does a really good job of showing kind of what things look like. And again, same deal here. This is a red dwarf flare star. It has, I think, 8% of the mass of the sun and something like 0.05% of its luminosity, right? So the amount of light that it puts out. So it's very dim. In fact, it's so dim and so small, they had to do a lot of work to make sure that it was actually a star, right, and not a brown dwarf. That kind of gives you an idea of how small it is. And it's not much, it's about the same size as Jupiter. So it's a little bit bigger than Jupiter, about 54 times more massive than Jupiter, right? That's kind of why it had enough mass to become a star. But anyway, these two are to scale, right? So this is TRAPPIST-1 here, the red dwarf. This is Jupiter. These are the orbits of the Galilean moons, and these are the orbits of the TRAPPIST planets, right? So you can see that at least the first, maybe, yeah, probably just the first planet in the TRAPPIST-1 system actually has an orbit the same as the orbit of Callisto, right? The outermost Galilean moon. So this is a tiny system, and if you put it to scale of our solar system, right, that's how big it is, right? So again, all of those planets are orbiting so close that they fit easily within the orbit of Mercury. But because that planet is, that star is so much cooler, and these planets are so much closer, the actual habitable zone is also an awful lot smaller, right? So if we go back to this image, for example, right, you can see the habitable zone around Proxima Centauri is tiny. The habitable zone of the sun is, you know, way out there, essentially. So even though this system is really tiny, right, the habitable zone is almost certainly around, just around these two planets here, D and E, right? And so, and they're also about the same, I mean, they vary between 60% and 120% of the Earth's density, and kind of around the same size, give or take. I think E is probably about the same size as Earth, right? So if you remember how I was talking about in the exoplanet search, how we're desperate to find, you know, even super Earths, right? But terrestrial planets, exoplanets, all of these, every single one of them is a terrestrial planet. They're all rocky. None of them are gas giants. I mean, they're not giants. None of them are gassy, right? Because they, by spectroscopy, they can't find any kind of hydrogen-dominated atmospheres. So that implies that it's not like a gas giant like Jupiter is. They all have similar densities to the Earth, so that implies a rocky planet, right, with potentially oceans. And yeah, and they all, and these ones orbit kind of within the habitable zone of, and this is again kind of struggle with font size. They don't seem to think about this very much when they make these diagrams, but it's a super cool image. So basically this is the two systems. Here's a TRAPPIST-1 system. This is our solar system. And they're rescaled based on essentially luminosity or received energy, right? So if you were to stand on the surface of one of these planets, how much energy would you be receiving compared to standing on the surface of the Earth, right? You know, would you be in shorts and t-shirts plus, you know, respirator maybe? Or would you be, you know, risking freezing to death, right? Or being boiled alive or whatever, right? And so essentially what they find is that, you know, there's a couple of planets here which are kind of between Mercury and Venus, right? And so they actually think there may be potentially one of these planets having a runaway greenhouse effect similar to Venus, maybe. Again, have to wait on better telescopes to find that stuff out. There's a couple which are more slightly similar to Mars, even though they're a lot more massive, right, compared to Mars. So that has a lot of interesting ramifications, right? Because if they're similarly massive to Earth, then they might have a magnetosphere. If they have a magnetosphere, they're going to potentially be protected against solar flares the same way we are, to some extent, against the solar flares from our sun, right? And then H, which is, I think, the smallest one of the system, is almost certainly frozen, right? Because it's at a similar distance in terms of energy from its star as asteroid belt. So that's kind of right on that frost line or ice line. So even though the TRAPPIST-1 is teeny tiny in kind of galactic terms, it has the same spread of terrestrial planets and environments, at least based on energy, as we have in our inner solar system here, you know, in this solar system, right? But it also has 7 rocky planets, not 3 or 4, not 4, sorry, I want to say 3, not 4. Right. So that's also super interesting, because for a bunch of different reasons, right? So there's a lot more chances that there will be a suitable environment in that system, right? Because instead of just having Earth, now we've got 2, maybe 3 planets, which should have a temperature similar to Earth, give or take. Obviously, don't know if they have atmospheres, don't know if they have water, don't know what effects their star would have had on those atmospheres, right? Mars had an atmosphere, it had water, and it lost it, right? Because it didn't have sufficient mass or a magnetosphere to retain its atmosphere. So do these have sufficient mass? Do they have magnetospheres? Does the increased flaring of their star negate that or not, right? Those are all kind of questions that need answering, right? And people are going to try and answer, particularly when the James Webb goes up, because it has a massive mirror to be able to look at stuff in much finer resolution, right, than either the Hubble or the Spitzer Space Telescope did. Actually, this mirror is super cool. You have to go look it up. But basically, it's a folding mirror, so it's kind of folds down to be able to get it sufficiently compact to stick it on a rocket. And then once it gets into space, it's going to open up like basically like petals of a flower. Super, super neat. And another really cool thing, and I'm just going to kind of make a bit of like a professor cop-out. Oh, actually, no, 2 cool things. I'll get to the second one in a little bit. So another cool thing is that these planets are potentially close enough to each other that panspermia may actually, if there is life in that system, it's much more likely that that life was able to get from one planet to another, right? Because when you look at this picture, this is only a slight exaggeration, right, of how close those planets, actually they would appear, in terms of planets, they would appear in the sky of any one of the other planets, probably 3 to 4 times the size of the moon, right? So if you think about the moon is about, I don't know, you hold up kind of a thumb, and it's about half a degree of our sky, right? And so these would appear at 2 to 4 degrees in terms of size, depending on which one you're on and which one you're looking at, right? So one kind of fun thing to think about is that if life did emerge on one of those planets, and you had asteroid impacts and things like that, it's quite possible that that life was able to get to another one of those planets in the system. Carol, what are you talking about? That's scary. You're the one that's proposing seeding planets with, terrestrial
Wait.
life.
It's just like you look at the moon, right, and it's so tiny, but like if it's that big, like what if it just crashes at any moment? You know what I mean? Like,
Well, actually, that's really interesting because of all these different bodies in the system, this 3-body resonance, it's actually a very stable system, right? Because even though some planets may kind of be inclined to move closer to their star, because there are other bodies in that system, they pull them back out, right? So those 7 planets are maintained in that system. It's a very stable system. And so even though they would look huge, the likelihood of them ever kind of crashing into you is 0, basically. Yeah, it's pretty funky. And it would just, it would be pretty mind-blowing. I mean, it would be more beyond mind-blowing to even go there and have a look at that. But this is a real cool thing. So because of that orbital resonance, some like uber astrophysicists, astrobiology nerds have basically turned that into music, right? So I'm just going to play you let's see if this works. A fun little video that some scientists up in Canada put together. Can you hear that?
No.
Okay,
Yeah, I can't hear anything.
that's okay. Well, you can play it afterwards. But where are we at? I just want to show you this. This is super, super cool. Blah. Let's get over that.
Wasn't that exactly Kiara's fear?
Oh, well, I mean, that happened to Earth, right? That's why we have the moon. Yeah, but I mean, it's kind of interesting. The more we study other solar systems, the more we begin to understand how solar systems form, and our kind of original understanding was kind of almost pitifully naive, right, based on our own solar system. And so there is an awful lot of movement, right? Actually, there's an awful lot we just don't know, but there's an awful lot of movement in terms of planets kind of in and out during solar system formation. We actually think almost positive that's the case in our own solar system. But because these resonance orbits are so stable, this I think they actually, if you watch the video, they say they modeled it out as far to infinity as they could using a supercomputing cluster, and they couldn't find any scenario in which this stability, this system broke down. Right, so they've actually tried to purposefully see if the TRAPPIST-1 system will stop, like if one of those planets will crash into another one. And now that it's attained that resonance, it, pending, obviously interruption from external source, it won't change, right? So it's an astonishingly stable system. So yeah, I don't know, you got to watch the video. It's really, really cool. But anyway, just watch this, right? This is kind of artificially starting them all at the same point. Isn't that crazy? Yeah, there you go. That's kind of what I was saying. But yeah, make sure you watch that video, because basically later on you see down at the bottom we've got these dashes. They put the orbits of, basically every time it rotates around the star, it gets like a piano hit, key hit. Hello, doggo. And then every time it passes another planet, it gets like a drum beat, and so on and so forth. And so actually they can make it into music, which is that's just it's a really interesting way of thinking about it, right? It's cool to see how other people can visualize complex systems, essentially. So anyway, essentially, like this is just a fascinating place to study. It really is. It's partly because of those that resonance, partly because there are, like, all of these planets are Earth-like, right? We're not just talking about one or two, right? They're all the same mass, density, and similar size to Venus and Earth, right? None of them are even as small as Mars, right? So they're all potential candidates for life, and at least two of them, maybe three or four of them, are potentially habitable. Potentially, right? Obviously, that depends on the behavior of the star and presence of magnetospheres and how strong those magnetospheres are and stuff like that. But if you wanted to go looking for life around, another star, TRAPPIST-1 system is, I would say, if you were putting money on it, that would be the safest bet. And it's not that far away. 40 light years is it's not too bad. I mean, that's like, I don't know, going to Lafayette for a po' boy. It's not terrible. You wouldn't want to do it on a regular basis, but it's not impossible either. So anyway, anybody have any questions? Hopefully your minds are suitably blown.
You're talking about driving to Lafayette, Louisiana?
Yeah, for a sandwich.
That's like the people in Queens that drove to Albany to get Thai food.
Could be, yeah. I mean, I've had po' boys in Lafayette. It was super cool. Kind of
Yeah,
weird.
better
I was
be-
driving
better
down
be
10 to go to Florida. Not be like, I'm gonna take a trip to Louisiana today.
Just because I'm really hungry, I'm craving a sandwich.
Yeah,
Yeah.
an authentic po' boy.
Yeah, I'm not really down on the whole idea of gravy and sandwiches. I didn't really understand that very much. It was a good experience, and I was not hungry at the end of it. That's for sure. But anyway, so yeah, that's pretty much that for these ones. Go to Galveston. I don't want to do that. Faster and same food. Okay. Yeah, but it's Galveston though. I don't know. Perhaps Galveston's a nice place. Everybody I've talked to about Galveston says, you know, don't bother going there.
The doctor brings up a great point. It is Galveston. Just go the extra distance to Lafayette.
I mean,
It's
if you're really,
okay. It's not beautiful, but if you want food, like it's closer.
if you really like oil refineries, I hear that it's like the absolute bomb of the place to go to. Like if you're like an oil refinery nerd, then Galveston's the right place. I don't know. Maybe Corpus Christi would be a bit better. I didn't think an awful lot of that when I went there either. Lafayette was super pretty though. Anyway, all right. Well, hopefully I've loaded you up enough. Oh, another cool picture. Before we go, there you go. That's what the sun looks like compared to TRAPPIST-1, or vice versa. It's tiny. If stars had inferiority complexes, TRAPPIST-1 would have one. Although I'd probably say, hey, 7 terrestrial planets, you've only got 4. Maybe it would, if it was in like a schoolyard fight or something, it would have a decent comeback. All right, ladies and gents, that's it from me. It would drive a giant truck. Yeah, that's right. Like 36-inch tires and smokestacks out the top. I am well versed in the ways of giant trucks. All right. Anybody got any questions? Anybody's brain capable of asking questions at the moment, or you need to like
Question.
let it go cool
So
down?
what exactly is the quiz on?
It's everything from last quiz to this quiz. What was
That didn't sound too exact.
okay, that's as precise as it needs to be, Jimmy. Where are we at? Where was the last quiz? Quiz 3. So it is basically Titan and Enceladus, a little bit on Saturn. We covered Jupiter already. What did we cover? Just trying to remember. We covered halophiles and psychrophiles after Titan and Enceladus, I'm pretty sure. And then essentially everything that we've learned about exoplanet hunting, exoplanet finding, and what we learned today. That's what will be on the quiz.
Thank you.
And maybe some sci-fi films as well.
Same thing as last time, 09 to 925.
Yes, that's right. Although if you do need to take it other time because of work commitments or scheduling or childcare or whatever, it will be available the whole day. So you don't have to take it at 9 o'clock in the morning if you don't want to.
Okay. Yes, sir. Appreciate that.
Yeah, I'll send out more details. I haven't actually written it yet. Kind of. I
That's
mean,
awesome.
kidding me? I finished this PowerPoint at like 12:30 last night.
Oh, it's all good. I'm not here to hate. I'm a procrastinator.
Yeah, I mean,
All right, appreciate you.
I'm a very efficient procrastinator, right? You know,
Oh,
I do
yeah.
each procrastination in turn.
Yeah, if you weren't, you wouldn't have the job.
That's right. But yeah, as soon as I've got details up, I'll probably I've got to record another lecture for my other course. So ideally get to it today. If not, obviously I'll get to it tomorrow.
Okay.
But yeah, it'll be available from 9 o'clock probably until midnight. Would be most likely like it was last time.
Awesome.
But
Appreciate it.
I'll definitely be around. I'll probably actually have a Zoom up on Friday morning during that 9 to 9:30 period. So if you do have any issues, I'm guaranteed to be there. Like if you need clarification on questions or something in the quiz doesn't work, I'll be available to kind of help with that instantly rather than emailing me and waiting for me to get back to you. So, also another thing about the quizzes, they're not forced completion. So if you do need to pause the quiz for any reason, even though they're technically 25 minutes, you can go back into them. It's not going to auto submit if you leave it. So, I mean, that's kind of, I don't know. I mean, I think we've been advised to be careful about forced completion, because if you drop your internet connection, it automatically submits your quiz or exam for you, which is not good, I don't think. So anyway, it's kind of giving you a little bit more details, probably more than I should do, but never mind. I'll cope. Anyway, see you, everybody, to infinity.
Bye. Thank you.
And beyond, as they say.
Have a
I'll
good
see you on
day.
Friday. You too.